So for 47.2, we are going to focus the periodic variation in melting point. Refer to the knowledge that you have learned in Chapter 9. You should remember that melting point depends on two things. Number one, they are depending on the structure. Number two, they are depending on the bonding. So therefore, every time when you try to explain the melting point difference, please referring to the structures and bonding the elements are having. So if we have a greater attractive force, then the melting point will then be higher because you need more energy to overcome the bonding. So you can have a look right here, So across the period, you will find that, we have lithium, beryllium, those are the giant metal structure. And then you have the purple one there, the giant covalent structure, and the last one in simple molecular structures. You should know that simple molecular structures, they're holding by van der Waals force, so the attraction need to be overcome have to be the smallest. So for the simple molecular structures, so you will find that, they will have a lower melting point comparing to the other two structures. While for the giant covalent structures, there are a large amount of bond needed to overcome in order to break down the giant covalent structure, the three-dimensional one. So therefore, this one normally will have a higher melting point than the giant metallic structure. So you have to remember that the covalent bond and the giant covalent structures will be more difficult to be overcome than the metallic bond and the giant metallic structures, and also the van der Waals force in the simple molecular structures will be the easiest one to overcome. So that will be the periodicity that we can see. We have a lower melting point and go to the high up, and then we just reach to the lowest. So if we try to present it in a graph, you will see something like this. So for the first two, that will be the giant metallic structures. We have the giant metallic structure for these two. And then we have giant covalent structure. We said that it will be relatively higher than the giant metal structure. And then it will go to the simple molecular structure because they are held by van der Waals force only, so therefore their melting point will be relatively low. After that, we'll get back to the giant metallic structure. We have sodium, magnesium, and aluminum here. And then we will go to the giant covalent structure. Last one, it will get back to the simple molecular structure. So you will find that giant covalent structure generally will have a higher melting point than the giant metallic structure, and then it will then go to the simple molecular structures. Now we're going to get deep into each of the structure and see why even giant metallic structure they will have different melting point. And also amount the simple molecular structure, they also have different melting point. We're going to see what happens right here. So for the giant metallic structure, before we move on, recall your memory. The giant metallic structure have the strong metallic bond. They are holding the sea of delocalized electrons and the cation together. So the cation and the delocalized electron are held together by a strong metallic bond. During the melting, you will find that not necessarily every single metallic bond have to be broken. So therefore, they are not substantially broken. That means not 100% of them have to be broken in order to make it into liquid metal. So therefore, this one will have a lower melting point, require less energy than those in the giant covalent structure. And for the strength of metallic bond, actually it depends on three things. The first one is the most important. The metallic bond, it will depend on the number of glues that we have in between. So these are the delocalized electrons. We will say that number of delocalized electrons participating in the metallic bond. So if we have like sodium, magnesium, and aluminum, you will notice that aluminum have 3 electrons, magnesium have 2 electrons, and sodium have 1 electron in the outermost shell. So aluminum will have a higher melting point than magnesium and then the sodium, in terms of this reason. Second one is about the size of cation. This one will be less important because you can't find that in the textbook, but that will be something I want you to remember as well. So for the size of cation, you will find that for sodium, if it is a cation, that will be definitely larger than that of lithium because lithium is period 2, this one is period 3. So therefore have one more shell of sodium, okay, than the one in the lithium. So for the size, we find that lithium will be smaller. If we say lithium is smaller, the charge density of lithium will then be higher than that of sodium, because the lithium is smaller, so the positive charge is more centralized in the middle, while the sodium, okay, they will have a larger cation size, so therefore they will be more dispersed. So we will find that the charge density of lithium is stronger, so therefore they attract the electron. The delocalized electron will be much stronger than the sodium. So we'll find that, okay, the lithium, okay, will then have a stronger attraction towards the delocalized electrons than sodium ion, than the potassium ion, because potassium ion has the largest cation size. Last one, okay, this one is LC, okay, that will be also related to the atoms, how the atoms are packed together. So this one, okay, that is part of the reason why aluminum and magnesium, okay, they have similar melting point in this, okay. So next, we're going to talk about the giant covalent structures, okay. So giant covalent structures, okay, record that strong covalent bond, which is a directional bond, because covalent bond is talking about the nuclei and shared electrons. So the strong covalent bond, they hold the atoms together. And remember, this one is a three-dimensional structure. If we need to break them up, okay, certain kind of quite a number of the covalent bond have to be broken. So you will find that, okay, in the process to break down a giant covalent structure, a large amount of covalent bond need to be overcome. So therefore, you need a lot of energy to overcome this kind of covalent bond. Finally, okay, it brings up to a very high melting point. Comparing to giant metallic structures, giant covalent structures with a higher melting point in this. Okay, and then finally we get to the simple molecular structures. Okay, simple molecular structures, we have weak van der Waals force only between the molecules. Remember, during melting, you're not necessary to break the covalent bond. Okay, you don't need to break this bonding. Okay, what you need to do is just separate the molecules. Okay, separate the molecules. So what you need to do is just overcoming the van der Waals forces. So what you have learned in microscopic world 2, you learn that, okay, the strength of van der Waals force, they will increases with the molecular size. That means larger molecular size, stronger van der Waals force. Okay, because of the uneven distributions of the electrons is have a greater chance. Okay, so therefore the van der Waals force will be stronger. Second one, okay, we'll not cover too much right here. Okay, that will be related to the area of contact. If you still remember, we have rod shape and spherical shape. So the rod-shaped one will have a larger area of contact, so therefore the van der Waals force will be stronger. Last one will be related to polarity of the molecules. But right here, okay, it is not that complicated, because we found that those are the elements. For elements, they're having the same elements, okay, the EM will be the same, so normally the electronegativity difference will be 0. Okay, so amount 3 of them, okay, will focus a lot on the molecular side. So one thing you have to remember is about the period 3 elements. So for the P, S, Cl, and Al, these 4 elements are very, very important, because we found that the molecular size are totally different. They are not diatomic molecule. When they form molecule, they have different number, different atomicity. If you remember the terms, you learn it in Form 4. Atomicity. So they have like 4 atom in it, 8 atom in it, 2 atom in it, and then 1 atom in it. So because they have different atomicity, so therefore you'll find that the atomic size, the size of the molecules will be different here. So due to size difference molecule size, you'll find that the melting point also in the sequence like this. Okay. So that will be the simple molecular structures. So now we get to this diagram. Now have a look one more time. Okay, remember several rules. Giant covalent structures stronger than giant metallic structure, stronger than simple molecular structure. So for period 2, okay, we'll find out the giant metallic structure. This one will have 1 electron involved, 2 electron involved. So Be will be stronger than lithium. Next, okay, that will go to the giant covalent structure part. Okay, so all the time diamond will have the highest covalent bond, and that will be highest melting point. That is so obvious. And then now we get to nitrogen, oxygen, fluorine, and also neon. Okay, so neon is monoatomic, so you will find that, okay, that will be lower melting point than NOF. Okay, but right here NOF, actually they are very, very similar. Okay, but precisely to describe, okay, you will find that F2 is weaker than O2, weaker than N2. You may ask that why it would be like that. Okay, it will be referring to the atom NOF. Isn't it F is larger than O than N? The answer is not. For the atom size, you'll find that N is larger than O and larger than F. So you can think about like this way. So if we have like electrons, all of them, they have electron shells, is that right? All of them, they have electron shell. For the F, you got like 9 proton in it. O, we got 8 proton. N, we got 7 proton. So for the proton to attract the electrons outside, you got electrons here, right? So the 9 proton one, they have more proton in the nucleus, so therefore the attraction will be stronger, okay, towards the center. So in this case, you will find that the atom radius will be smaller. Okay. While the nitrogen, they have less proton in the middle, so therefore they will be less, the electrons in the outermost shell will be less likely to pull to the center. So you'll find that the atom size N will be much larger than F. If N is larger than F, then N2 will also be larger than F. Okay, the size, okay, N2 will be larger than F. If N2 size is larger than F, of course, the melting point of the nitrogen will also slightly higher than F. Okay, but I think the details for this part, okay, is not really necessary in DSE, but I just want to tell you about that. Okay, but you have to know that NOF should be larger than Fe. Okay, because those are diatomic molecule, while this one is monoatomic molecule. Okay, so now get to the period 3. So period 3, okay, you got sodium, which have 1 electron, magnesium we got 2 electron, and aluminium we got 3 electron. So Al is slightly larger than Mg. Okay, so in terms of like the delocalized electron participating in the metallic bond, the more number of delocalized electron, the higher the melting point. So this one is still valid. Okay, you see that 3 larger than 2 larger than 1. Okay, slightly higher. So slightly higher. Okay, so and then we get back to the structure. So next, okay, go to giant covalent structure, must be the highest, and then finally we come to the simple molecular structures. Amount the whole or all these elements. Okay, this section is the most important because it always asks. Okay, so one more time you check it. Okay, we got a very special shape at that. If you recall, S will be S8, P will be P4, Cl will be Cl2, Ar will be the lowest Ar. So you find that S8 have larger molecular size than P4, so this one will be higher than that, and P4 will have a larger molecular size than Cl2, so this one is slightly higher than Cl2. Okay, and the Ar is monoatomic, so therefore it will be the lowest. So this section is always asked. Okay, so do remember you need to sketch this part as well. Actually, not only this part, the whole diagram. So for the whole graph, okay, you have to sketch. Okay, for different sections. Okay, so next we're going to have one example in page 10. Okay, so you'll find that we're talking about the phosphorus, sulfurous, chlorine, argon. We compare this. Okay, and then we're going to, what type of attractive force must be overcome when each of the elements are melted. So remember the attractive force when the simple molecular structures are melting. We are talking about the van der Waals force only, not the covalent bond. Remember, not the covalent bond. Okay. Next, judging from the formula, arrange the elements in decreasing order of the molecular size. Pretty simple. 8, 4, 2, 1. Okay. And then, okay, we're going to base on this, okay, arrange the elements in decreasing order of melting point. So decreasing order, so you will find that the molecular size the strength of van der Waals force will increases with the molecular size. So the keywords goes to larger the molecular size, stronger will the van der Waals force. Okay, so therefore this will have a higher melting point of the element. Okay, so you arrange them, okay, in the sequence of the molecular size, then you can tell the melting point of them. Okay, so lastly, okay, I remind you, okay, you have to learn how to draw the structure of these two molecules. One is P4, one is S8. Okay. So before we end this videos, we're going to do one more class practice. These are some typical questions that you may see in DSE. So they will give you a table telling you that, okay, the melting point of different elements. So based on this table, you're going to try to explain the differences in the melting point, okay? So the first one is talking about the lithium, beryllium, and boron. Because we got 3 items there, so normally you can separate them, okay, with A, B, C, them, okay? So you try to separate them into 2 paragraphs. Maybe you say that, oh, C is larger than A and B, and then you compare A, B. Okay, so have a look. Okay, boron, beryllium, and lithium. So for lithium and beryllium, they are giant metallic structure, while boron, okay, very similar to the carbon, they are giant covalent structure. So by doing this, okay, you can tell. Okay, melting point must be talking about 2 things: 1, bonding; 2, structure. Okay, so you try to describe boron like talking about the structure, giant covalent structure. Atoms I have to go about strong covalent bond. Okay, that will be stronger. Okay, will require more energy than the giant metallic structure one. Okay, so therefore for the boron, okay, you may say highest melting point because they have a giant covalent structures for breaking down the many covalent bond between the atoms. Okay, so therefore more energy required than to melt lithium and beryllium. Okay, so that one will be for boron. Next, you talk about the lithium and beryllium. Remember, lithium, they have 1 electrons participating in the melting a metallic bond, while beryllium you got 2. Okay, so therefore more delocalized electrons participating in the metallic bond, the stronger the metallic bond, and then more energy required to do. So you can find that these 2, they have giant metallic structures. Beryllium have a higher melting point because more delocalized electrons. Okay, more delocalized electrons participating in the metallic bond. Okay, so therefore the metallic bond will be stronger than those in lithium. Okay, and then you talk about the energy. Okay, so you can either talk about the boron come first, or you may talk about lithium and beryllium go first. Okay, so either one of them will do. Part B, okay, you're going to talk about the differences between the nitrogen and neon. That one is simple. Okay, nitrogen, okay, it is N2, neon is Ne. So the keyword, it must be talking about the diatomic molecule and also the monoatomic molecule. Okay, but remember, okay, that one, okay, again, you have to talk about the bonding and structure. The structure is simple monoatomic structure. The bonding is van der Waals force. Van der Waals force will increases with the molecular size. So therefore, you have to mention like molecular size, or larger nitrogen have a larger molecular size. Maybe you talk about diatomic molecule or monoatomic molecule, and then you say that, okay, strength of van der Waals force increases with molecular size. So these are some common statement that you must mention, okay, in the explanations. Okay, so therefore more energy required to do. Okay, so this part, okay, I encourage you to write once, okay, and then you check the points, okay, with the marking here. So conclusions, okay, the variation in melting point, the melting point will depend on bonding and structure. All the time you talk about the structure and bonding. Okay, remember, normally structure go first. Okay, structure and bonding. Okay, and then the greater attractive force, okay, the higher the melting points. Okay, normally covalent bond in GCS we have we need to break more covalent bonds. So therefore, we talk about GCS will be stronger than that, higher melting point than GMS, and higher melting point than the SMS. And for metallic bond, okay, the metallic bond depends on the delocalized electron number of delocalized electrons participating in the metallic bond. That is the most important part. Okay, so therefore you find that Al3 plus Mg and also the Na. Okay, so the number of electrons in aluminum have 3, magnesium have 2, sodium have 1. Okay, number 2, okay, you talk about the size of cation. Okay, so lithium ion will be smaller than sodium ion, so therefore it will be much more stronger than that. Okay, so smaller than sodium ion, so therefore the attraction will be stronger. Number 3, it will be the how the atoms are packed. Okay, but this one will be how the atoms are packed, but this one will be out C. Okay, and then for the van der Waals force, okay, we have 3. One is the size of molecule. Okay, number 2 is the shape of the molecule. Okay, that will be related to the area of contact. Number 3 will be the polarity. Okay, so these are the things that will affecting the strength of van der Waals force. Okay, lastly, remember you have to sketch the trend of the melting point. The most important part should be this area. Okay, normally for the giant metal structures, keep on going up will do. Okay, remember every point you use a cross to represent the data. Okay, so that will be what you have to learn in 47.2. Bye bye.